a row-reduced form of a matrix, one has each row consisting entirely of zeros lies below any other row having non-zero entries. The first non-zero entry in each row is 1, called a leading one. In any two successive non-zero rows, the leading one is in the lower row lies to the right. They're giving you this really long description, but basically, to show you, if I were to have a matrix that's 2 by 2, and these have to be square matrices, by the way. A 2 by 2 square matrix looks like this for a row-reduced form. A 3 by 3 looks like this. A 4 by 4 would look like this. Basically, all I'm going to have are ones and zeros, and the ones start at the upper left-hand corner of the matrix and move in a diagonal pattern until it reaches the bottom right. So essentially, you'll see them sometimes even represented as 1, 0, dot, 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 0, 0, 1, dot, 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 0, and it'll say dot, they'll do all these little dots and stuff like that. To eventually have 0, 0, dot, 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 1 here. And they kind of show it like that, showing that you're going to have a diagonal of ones and all the other row column entries are going to be zeros. That's what they call row reduced form. And that's what we want to end up with on the left-hand side. Because remember, each column represents usually a variable. Okay, so if I have 1x, 0y, 0z's equaling a number, well, that means that x equals that number. So, and, but the thing is, you have these row operations to do it, which looks a lot like the elimination rules. I mean, I can interchange any two rows because that's the same thing as interchanging two different equations. I can replace any row by a non-zero constant multiple of itself. So I can multiply any row by a constant. And I can also replace any row by the sum of that row in a constant multiple of any other row. So it's kind of the same thing I do with elimination, and that's why they call this usually like, matrix elimination method. So, and that's what the Gauss-Jordan elimination method does. It's basically, when you take an augmented matrix and you make the left-hand side into a row-reduced matrix, that's basically what you're doing here. The trick of doing this is, even though these are what you're allowed to do, and they're showing you like the context, the symbolism that you would use to do it. Like if I have like a row, like row 1, double arrow, row 2, it means I'm interchanging those two rows. If I have a number times row whatever number it is, I'm replacing that row with a number times that row. And this one's very important too, the last one. If I start with, like, if I have row I plus a multiple of row j, means I'm replacing row I with the sum of row I plus that multiple of row j. Which, I mean, so, and it doesn't have to be a consecutive rows. I could take the first row and add it as a multiple of the fourth row, or whatever it may be. The thing is that students sometimes have trouble with this, is that you have to do this in a very specific way. Otherwise, you could possibly have row operations that will undo the effects you wanted to have in any other row operation. So let me demonstrate for these two. This is the same 2 by 2 matrix we had before. So no big deal about that. I mean, we should get the same answers we had before. So I'm going to rewrite this and as an augmented matrix. And now what I want to do is get this side here. If I can get my cursor over there. Come on. There we go. I want to get this row, this side right here to be that 1, 0, 0, 1. I mean, so that's what my goal is. My goal is to make it look like that. I already have the 1 in the upper left-hand corner, so that's one less thing I have to do. What I want to do now is that's the way it works. I establish the 1 where I need it for a given column first. So I do row operations to alter each column, going column by column. So I want column 1 to get this 1, 0 look to it. I have the 1, I want a 0 down here. The row operation I am typically going to use to get a 0 in the position I need it to is to replace the row I'm looking at, in this case row 2, with a multiple of any other row in the matrix. We only have one other row here. So if I were to take 2 and add it -2 times this 1, I would get a 0 there. Well, that's what I'm going to do. I'm going to take row 2 and I'm going to multiply. I'm going to basically add a -2 times row 1, or basically say here, I'm taking row 2 and subtracting 2 times row 1. Remember, in algebra, adding and subtracting are considered to be the same. They're the same in the precedence of order of operations because they're the same operation. All subtraction is essentially adding a negative. So this is legal. So if I take this 2 and subtract away 2 times 1, I do get the 0. 3 minus 2 times -2, well, 2 times -2 is a -4. If I take 3 minus a -4, that's 3 plus 4, that's 7. 8 minus 2 times -3. 2 times -3 is -6, so 8 minus a -6 is like the same thing as 8 plus 6, that's 14. So now I have this column. The next thing I want to do is establish a 1 down here. The best way to establish my 1s is that's where I usually am going to multiply by a constant times the row. So here I'm going to take row 2 and multiply it by 1/7, which is the same thing as dividing by 7. So if I do that, now row 1 is unaffected. 0 times 1/7, nothing happens. And that's what I want to have happen. Once I get that 0 here, and once I have this column established, any change I do from here on out should leave that column alone. If I am not doing that, if that's not happening, if I get that column to change in any way, I'm undoing some of the things I've done before, and I'm not going to get the answer I'm looking for. 7 times 1/7 is 1. 14 times 1/7 is 2. So I got this right here. Now, this is what we would call reduced form. And actually right now, I have a statement that says 0x plus 1y equals 2. So I know what y equals. I could find x at that point if I wanted to. But they want you to put this in this form so that when I have the end of product, I can say I have 1x equaling a number, 1y equaling a number, so I know what they are. So now I want to get this to be a 0. Well, again, to get zeros, that's when I add a multiple of another column. So I want to take row 1 of another row. So I want row 1 to be replaced by row 1 plus 2 times row 2, because if I take -2 plus 2, I'm going to get that 0. And so that's what I'm going to do here. I'm taking row 1 and I'm adding 2 times row 2. So if I take 1 plus 2 times 0, I'm still going to end up with 1. Good, that's unchanged. I don't want that to change. If I take -2 and add 2 times this, well, I'm going to get that 0. Well, that's what I wanted there. -3 plus 2 times 2, well, 2 times 2 is 4, so -3 plus 4 is 1. So I have 1, 0, 0, 1 on the left. I have 1, 2, which means, again, at this point, I have 1x plus 0y's equaling 1, which means x equals 1. And I have 0x's plus 1y equaling 2, which means y equals 2. And I get the same solution I had before. And that shouldn't be no big surprise because I should get the same thing I had before. Okay, so again, there could be variations to this, but this is how I approach doing it. So keep that in mind if you did some other similar things. but went some different routes with it, that's fine too. The first thing I did is, I obviously want to turn the 2 in the upper left-hand corner into a 1. So I'm going to take the entire row 1 and essentially divide it by 2, or multiply by half, same thing. So my first row becomes 1, 1.5, negative 1, and a 5 on the other side of the line. The other 2 rows were unaffected because I didn't do anything to them. So I established the 1 where I need it to be. Now I need the 3 and the 4 underneath that 1 to become zeros. And I'm going to do that by taking row 2 and row 3 and adding some multiple of row 1 to it. So row 2, I'm going to take row 2 and subtract away 3 times row 1. I'm going to take row 3 and subtract away 4 times row 1. And I do both of those together. I mean, technically they're 2 different row operations, but row 1 is being unaffected. I'm only using row 1 to get a multiple of it. If I'm taking row 2 and subtracting 3 times row 1 from it, I'm going to get a change in row 2. Same thing with row 3. So if I carry through those operations, 3 minus 3 times 1 is 0. Negative 2 minus 3 times 1.5 is a negative 6.5. 2 minus 3 times negative 1 is 5. 0 minus 3 times 5 is a negative 15. 4 minus 4 times 1 gives me the other 0. Negative 1 minus 4 times 1.5 gives me negative 7. 3 minus 4 times negative 1 gives me 7. And negative 1 minus 4 times 5 gives me a negative 21. So I've established my column 1 with the 1, 0, 0 I want. Now, any row operations I do after this point, that column should remain unaffected. If I'm doing something that makes that column change in any way beyond it being the 1, 0, 0 I have going from top to bottom, then I'm doing some incorrect row operations. So the next thing I want to do is I want to establish the 1 I should have right here. So what I want to do is essentially divide row 2 by a negative 6.5, which is the same effect as me, if I get to work, taking negative 2/13 times row 2. So 0 times negative 2 over 13 remains 0, unchanged. Negative 6.5 times negative 2/13 will give me the 1. 5 times negative 2/13 gives me a negative 10/13. And negative 15 times a negative 2/13 gives me a positive 30 over 13. Get some nasty fractions here, and oftentimes when you're using this method you will, but it's still keeping things rather organized. So now I've established the 1 down here. I want to make this and this zeros. So I'm going to take row 1 and add it by a multiple of row 2, and I'm going to do the same thing with row 3. So essentially, since 1.5 is 1.5, I'm going to make that at 0. I'm going to take 1.5 minus 1.5 times 1, which tells me I'm going to be doing row 1 minus 1.5 times row 2. In the very similar nature, I want negative 7 plus 7. That'll cancel, become a 0. So I'm going to do row 3 plus 7 times row 1. And that's what my 2 row operations are. And when I carry them through, these are what I get. I get my column of 0, 1, 0 here. This becomes a 2/13. This becomes a 21 over 13. This becomes a 20 over 13. This becomes a negative 63 over 13. Row 2 was left unchanged because I just used a multiple of row 2 to help me. Now again, when I carry through any other row operations to the rest of this problem, this column as well as this column should remain unchanged. If that's changing as I keep doing more work, I'm doing incorrect row operations, or I'm not doing them in the proper place at the very least. So now I want this to become the 1 that needs to be at this corner. So to turn this into a 1, I would multiply it by 13 over 21, which means I'm going to take this entire row. and multiply it by 13 over 21. So when I do that, I get the 0, 0, 1 here. Negative 63 over 13 times 13 over 21 becomes negative 3. So I have my 1 established in column 3. Now I need these to become 0 and 0. So the row operations I choose to do is I'm going to take row 1, which has the 2/13ths. I'm going to subtract that by 2/13ths times row 3, because that has the 1 in it. And I'm going to take row 2, which has a negative 10/13ths, and I'm going to add 10/13ths times row 3, because negative 10/13ths times 10/13ths times 1 would make that a 0. So if I carry through these operations, I do get that format on the left-hand side. The 20/13ths minus 2/13ths times negative 3 is going to give me 2. And the 30/13ths plus 10/13ths times negative 3 gives me a 0. So again, I have the x, y, and z that I had there before. So my solution is still going to be 2, 0, negative 3.